When we were younger, we thought everyone was on our side. And then we grew a little and romanticized. About the time I saw flowers in your hair. Takes a boy to live, takes a man to pretend he was there. And then we grew a little, learned a lot. And then we demonstrated it to the cops, and all the things we said, we were self-assured. It's a long road to wisdom, it's a short path to being ignored. Be my eyes, be my heart, be my eyes, aye, 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 be my heart, be my eyes, be my heart. All right, hey, welcome you guys. Again, thanks for hanging in there with me. This will be our last acids and bases thing, and I just noticed a typo here. Man, I thought I fixed everything. This is actually day 5 of acids and bases, and this will be our very last lesson of the year. Thanks for tuning in, you guys, and the few of you that are hanging in there with me. But yeah, so we're going to just talk about buffer solutions today and how to make one. This is just a really basic thing in chemistry, and actually buffer solutions are all around us. We make them often, and our body uses them to maintain pH in our blood and things like that. So let's get going here. All right. So I just want to review this with you guys, acid-base reactions. So whenever we have a strong acid or a strong base, the reactions go to completion. There's no equilibrium. The equilibrium is going to lie completely to the right or to the product side. So for example, if we have a weak acid like hydrogen fluoride right here, we have a strong base like sodium hydroxide, this reaction is going to go completely here to the product side, right, when we'll get all water and sodium fluoride. And that's because of this, because this strong base here, this strong hydroxide, it's going to take or rip the hydrogens off of the hydrogen fluoride, right, until they're all completely used up. All right. Same thing goes if we have a strong acid like hydrochloric acid here and ammonium. If we combine those, right, ammonium, hydrochloric acid is a proton donator, and it wants to donate these protons. This is an acceptor. Well, we are going to go completely to the right-hand side here with the products. Okay, so keep that in mind. Now, the other thing about acid-base reactions I want you to remember is this, is that when you have weak acids and weak bases, the dissociation favors the reactants, favors the opposite side, right? So when we have acetic acid here reacting when we put it in water, okay, we only get a small percentage of product, a small percentage of hydronium or hydrogen ions being produced. Okay, so the reactants are favored. All right, same thing when we have weak bases, right, such as ammonium. Okay, it is definitely favors the left-hand side here, the reactants. Okay. Now, what is a buffer solution? So a buffer solution is this, you guys. It's a solution that resists change in pH. It'd be cool if we could do this. I'm not in my room today, so can't do it for you. But basically, it's, you know, if we put small concentration, so if we add drop by drop, say some hydrochloric acid to a buffer solution, the pH will change very little. If we were just to add drop by drop hydrochloric acid to just a water solution, the pH would change very quickly, very drastically. Okay, so buffer solutions resist change in pH, okay, for small quantities of acids or bases. So how do we do that, and what's in it? Well, here's the deal. Buffer solutions contain a weak acid and its salt. For example, hydrogen fluoride or hydrofluoric acid, right, and potassium fluoride. Okay, so this F here, that's the conjugate base, right? And since potassium fluoride is highly soluble when we put that in solution, this K here basically becomes a spectator ion and doesn't really participate in any kind of reaction. Okay. All right, the other thing we could do is this, is we can make a buffer solution with a weak base and its salt. For example, we could use ammonium and ammonium chloride, right? Ammonia, excuse me, and ammonium chloride, okay? So either way, and why is that? Well, let's explore that real quick. How do buffers work? Well, we've got this. If you have a weak acid, for example, acetic acid, remember the equilibrium lies to the left over here, okay? And if we have its salt, right, its salt completely dissociates. So that means this, right, when we have a solution, we're going to have a buffer solution, excuse me, you're going to have lots, if we put weak acid in it, we're going to have lots of weak acid in its undissociated form. And if we put its salt in with its conjugate base, it's totally soluble. So we're going to also, on the flip side, have lots of conjugate base to react with any kind of acid. So that means this, we've got lots of acid, right? Lots of acid here to react with strong bases, okay? And we also, on the flip side, have lots of conjugate base to react with strong acids. So therefore, when we add either of those things, right, strong acids or strong bases in, the system can react with those and neutralize them without changing pH very much. There we go. Took a couple clicks there. So when we talk about buffers, we also have this, we have buffering capacity. So that's the ability of a buffered solution to accept the protons or hydroxide ions without significant pH change. You can always overload a buffer system, right? Just by adding lots of acid or lots of base, and that can change things quickly. However, we talk about buffering capacity, and buffering capacity means this: if we can make the concentration of our buffered solution higher, we have more buffering capacity. That means we're going to have more moles of weak acid and more moles of conjugate base in that buffering solution, which means it will be able to absorb more hydroxide or hydrogen without changing pH. Now, when we talk about buffers, and we'll talk about this as we talk about making those solutions, the best buffers have equal or close to equal concentrations of acid and conjugate base. All right, and we'll talk about that here in a second. All right, this is our fun equation for this one. Now, I won't make you do this a whole ton. I've got an example on here. I'm going to ask you to do this for one problem. Okay, you guys, this is our last assignment, so it's not going to be like huge or long. Just want to give you a little taste here. Okay, so here's the deal. This is called the Henderson-Hasselbalch equation, right? You can see here how all the components, right? We got pH, so the desired pH of the buffer solution. Buffer solutions, you guys, are set at certain pHs. In fact, I can order them from chemical companies. Hey, I want a buffered solution that has a pH of 4, and I can get that. Okay, I could also make that, and that's what we're going to kind of look at today. This pKa right here is the pKa of the weak acid or weak base that we're going to use. And then it's the natural log of the concentration of the salt, the conjugate base on top, and the concentration of the weak acid on the bottom. So I'll show you how to use that in a little bit. Let's explore this equation some first, though. Okay, so the first thing is this: we need to choose buffer pairs. So here's our equation. Now here's the deal. When the concentrations are equal to 1, then the log of 1 is 0. Right? Those of you that are familiar with log base 10, the log of 1 is 0. And that means that the pH equals the pKa. And that makes things very simple. And it also helps us choose which acid we're going to use. If you go on Google and you type in pKa table for acids, you'll get a whole list of acids that have pKa's that range from into the negatives all the way up to 10 or 11. And so so we can choose a weak acid for our buffer solution that's going to be close to our desired pH. Okay, so what does that mean? Well, that means this. I got to get moving a little bit here. When we have a pH of 3, if I want to buffer, I'm going to choose benzoic acid, right? Because it has a pK of 3.18. It's really close. If I want a pH of 5, probably going to choose acetic acid here, right? Because it has a pKa of 4.74. If I want a pH of 9, I'm going to choose hydrocyanic acid because its pKa is 9.21. Okay. If I wanted a pH of 7, I'd probably choose hypochlorous acid or something like that. Okay. All right. The other thing is this, folks, adjusting the pH of buffered solution. So when this is 10 times, like when the ratio of these is this at the top is 10 to 1, our log is 1, right? When our ratio is 1 to 10, our log is -1. So we can make large adjustments, right? We can make adjustments that don't, I don't know. You kind of get what I'm saying here, you guys, right? That large adjustments in these can have a, not a big impact on our overall pKa and equation here. I didn't explain that very well. Hopefully you get what I'm saying. All right. So here's the deal. Comparing the pH and pKa provides info about the ratio. This is really what I want to get to. When the pH is less than the pKa, then our acid on the bottom is going to be higher concentration. If the pH is larger than our pKa, the base on top, the conjugate base, will be greater. Okay. All right. Here's our one big example problem. All right. See if I can find a place to put my face here without getting in the way. So we want to create a buffered solution where the acid and its salt have similar concentrations, right? So we're going to calculate the ratio of concentrations, okay, that are necessary to produce initial pH of 4.7, okay, and that's resistant to a change in pH when 1.1 moles of NaOH is added. Now, just a note, you guys, we want our concentration of buffer to be at least double that of the acid or base that we want it to buffer against. Okay, and I'll talk about that more as we work through this equation. So I'm going to choose this. I'm going to choose acetic acid because it has a pKa of 4.74, and if we want a pH of 4.7, that's super duper close, man. Okay, so here is our Henderson-Hasselbalch equation, right? And here is our Henderson-Hasselbalch equation with values plugged in. So I plugged in the pH that I want. I plugged in the pKa of the weak acid, acetic acid, that we're going to use. And I plugged in down here, I want 0.2 molar of the acetic acid, right? So that I can deal with the 0.1 moles of NaOH. That way I have extra wiggle room, right? And so that before I run out of acid or base. Okay, so start solving this, right? So I subtract, okay, and I get 0.04. Then I reverse the log, right? And I do that by doing 10 to the negative 0.04. When I do that, I get this 0.912 is equal to point A over 0.2. Okay, and then when I solve it, I get 0.18 molar. So that tells me the concentration of my acid or base on top. Okay, so that means this, the buffer will have 0.2 molar, right, acetic acid, and 0.18 molar sodium acetate, okay, because that is my conjugate base I'm going to put on top. By the way, if you're wondering, when we use those conjugate bases, we're always going to use like potassium or sodium as the positive ion that goes with it, because those tend to be extremely soluble and won't come out of solution no matter really what you react them with. Okay. All right. Well, thanks for tuning in, you guys. It has been a blast this year. I will miss you guys. Please, if you're around, stop by and say hello next year. And yeah, maybe I'll run into you too around this summer. So take care, and we'll see you later. Bye-bye.